All right, so number one, a guidance counselor is interested in comparing GPA of students with home access to internet, students who do not have this access. She pulled the files of a simple random sample of 10 students who have home access to the internet and a simple random sample of 10 who do not, and proceeds to run a t-test to compare the mean GPAs. All right. Which of the following is a necessary assumption? Well, we're working with the small sample sizes. All right, so we can't do normal by central limit theorem. So for things to be the case, we need a random sample. Less than 10% of the population probably is, but we also need to make sure that the underlying distribution is normally distributed. So in this case, we would need to graph them and check our box plots to make sure they were in fact normally distributed. All right, resuming recording number 2. Which of the following is a true statement? Tests of significance are designed to measure the strength of evidence against the null hypothesis. Guess what? That was really nice. That's actually true. We do not gather evidence to prove the null. We never gather evidence to prove the null. We don't gather evidence to prove the alternative. We gather evidence against the null. So the key phrase here is against the null, because we gather evidence against the null. The prosecution does not gather evidence to prove the defendant innocent. It gathers evidence to prove them guilty. All right. It gathers evidence against innocence. All right, in general, how does doubling the sample size change the confidence interval size? In general, how does doubling the sample size change the confidence interval size? Well, let's look at our formula. So T equals X bar minus mu S divided by the square root of N. So as it turns out, if we double the sample, if we increase N, as N goes up, the width goes this way. Why? Our error decreases. So we're going to make our error smaller. All right. So we're not going to double the size. We are going to divide. We're not going to multiply. So we have halve and divide, because those are all possibilities. But this is here. This is underneath. So we're taking the square root of our sample size. So if I double it, what I'm actually going to do is divide by 1.414, because the square root of 2 is 1.414. So my interval is going to decrease in width by 1.414. And I want to pause for just a moment, because I'm going to give you a little formula here. Okay, so here's a little formula on the way things happen. If we say that this is our interval width, it's going to go from the square root of our original over our new. So if this is our interval width, our original interval width, what's going to happen? Well, if our original happened to be of size, I don't know, let's say 8, and we doubled it, that would be 16. So that would be 8 over 16 is 1/2. And when I do that, I end up dividing by 1.414. All right. You know what? I'm sorry. I wrote this totally backwards. I cannot believe I did that. I apologize. It's new over original. That's what I was doing wrong. New over original, 1 over that. That's your ratio. So had we started off with an original of 8 and gone to 16, 8 goes into 16 twice. So this would have been 1 over the square root of 2, which is 1 over 1.414. So we're dividing by that. Why is that important? Because if we were doing multiple choice tests, which we're not right now, let's just say we had the same formula, 1 over the square root of nu, because if we were doing multiple choice tests, you would be seeing this. 1 over the square root of, let's just say our original was 9, and we went to a sample size 81. Well, 9 goes into 81 9 times, so that'd be 1 over the square root of 9, which would be 1/3. So as we increase our interval, we're going to divide by, as we increase interval size from 9 to 81, our width of our interval becomes 1/3 as wide. And if you go the opposite direction, that formula still works. So the thing is nu over original, and it's 1 over that. All right. A confidence interval estimate is determined from the summer earnings of a simple random sample of n students. All other things being equal, which of the following will result in a smaller margin of error? So let's talk about margin of error. First off, x bar plus or minus t star s divided by square root of n. This area right here is my margin of error. So as t star gets bigger, t star goes up. Let me do that a little different. Margin of error. That goes up if t star goes up, or if s goes up, or if n goes down. So we want a smaller margin of error. We want a smaller margin of error. So this needs to go down. So that means t star would need to go down, s would need to go down, and n would need to go up. So all other things being equal, which of the following will result in a smaller margin of error? A greater confidence level. Well, that's going to make a bigger t star. So that's not true. A larger sample standard deviation. If that goes up, this goes up. So that's wrong. A larger sample size. If that goes up, this goes down. So number 6 is letter C. And that's actually a pretty important concept. Number 7, which of the following statements is true? It is helpful to examine your data before deciding on using a 1 or 2-sided hypothesis test. Good statisticians never examine their data. They determine what type of tests they're going to run before they do anything. It's like, oh, we're going to do a one sample, we're going to do a 1-sided test, we're going to do a 2-sided test. Looking at your data, examining your data is kind of like cheating. Reality happens all the time, but ideally you're unbiased and you don't look at it until after. You don't look at your data, you just decide beforehand. If the p-value is 0.05, the probability the null is correct is 0.05. That's false. P-value is a probability you get a test statistic as extreme or more extreme given the null is true. So if the null is true, there's a 5% chance we'd get a test statistic like this. So that's false. The larger the p-value, the less evidence there is. All right, the smaller the p-value, the more, but the larger, the less. So this is also wrong. If the p-value is small enough, we can conclude the alternative is true. That's really a tricky statement. If the p-value is small enough, we reject the null. Remember, in statistics, we never prove anything true. We're just negative people. We're looking for false. So if the p-value is small enough, we can conclude the alternative. We reject the null in favor of the alternative, but we never prove it's true. So that's false. That one's tricky. We do not use sample statistics in stating the hypothesis. Remember, our hypothesis is stated with mu equals. That is a population. This is an X bar. We never use X bar or its values for the hypothesis. So this is the true statement. So number 7 is the true. Number 7E is the correct